have an Excel spreadsheet, which basically represents Practice Lab 3. The spreadsheet has 3 different tabs, 3 different worksheets. That basically are the examples that we're playing around with today. We also will need R, and there is an R script that is called Practice Lab 3 Solution, posted on Canvas. If you go all the way down, that was a skeptic look. Do you find it if you go down on Canvas? No? Did you find it? Oh, no. Okay. So if you go on Canvas, it should be of today's module. At the very end. At the very end, there should be Practice Lab 3, homework out of class. This is out of class, but we're doing it in class. So there's Practice Lab 3 solution.r. Do you find that? If you download that and you open it in R Studio, notably R Studio, not R, you will have this view, which is basically code walking you through all 3 examples that we'll be doing today. Good. As a quick entry into the topic, just again, a quick recap. And this is quite an important again, a quick overview of different tests we've done so far. So we did hypothesis testing using the normal distribution, the SAT test, SAT statistics, and we started doing t-distribution using t-tests. So in a SAT test, you have one sample and you compare the sample mean to a population mean, which is super simple. And you basically, what will prompt you to think of a normal distribution or a SAT statistic is that you have a sample size greater than 30 and a normal distribution, and you have the standard deviation given from the population. The standard deviation of the population is given. Whereas with t-test, you basically are estimating that standard deviation from the sample with the simplest form. So the distribution, the comparison distribution is the distribution of means, which we quantify with the standard error of the mean. We're comparing the sample mean to the population. In a single sample t-test, we do the same thing. We have one sample, and we're comparing that sample mean to our population mean, utilizing an estimated standard deviation, which is different from the standard deviation in population, where we have a division of the sum of squares, which is the deviations of each individual score from the mean. Each individual of these deviations squared, summed up, gives you the sum of squares. And if you have a distribution of a population, you divide it by the sample size, whereas for a sample where you mean to estimate the population standard deviation, you divide by the degrees of freedom, which is the sample size minus 1. Right? That was the distinction between the standard deviation in the sample and the population. Good. In a single sample t-test, you have one sample, you have one mean, and you're comparing that mean to the population mean. And you're doing that by basically estimating standard deviation based on the sample standard deviation under the assumption that this will reflect the population standard deviation from which you sampled that sample. And you're basically comparing that sample mean to the population mean by utilizing t-statistics and calculating the difference from the sample mean to the population mean and standardizing this difference by the standard error of the mean. The paired sample t-test and the independent sample t-test, both you have 2 samples, whereas for the paired sample t-test, these are paired, meaning it's the same participants, it's the same subjects in your sample in a before and after situation. You basically calculate individual differences, so you get individual scores and your degree of freedom there. This is a mistake I've seen repeatedly. Please don't make this mistake on the quizzes or finals. The degree of freedom of a paired sample t-test is your number of differences, the different scores. Each participant produces one difference. before and after. The degree of freedom of that is the number of different scores minus 1. Whereas with an independent sample t-test, you basically have two different samples, two different cohorts, different individual those two. They're independent from each other. And the degrees of freedom are the number of all participants in both samples minus 1 for each sample. So it's minus 2. That's your degree of freedom in an independent sample t-test. That's an important distinction. The comparison distribution for paired sample t-test is the distribution of the mean difference scores. So you calculate those mean difference scores, you calculate a mean difference, and you standardize that mean difference. Whereas with the independent sample t-test, you're calculating the differences between means. So the distribution of the differences between means is your comparison distribution. So the idea is that you have two independent samples. You sample from both of these samples. You calculate the difference. You have one difference. You drop those samples back, and you do that again. You randomly sample those repeatedly, and you get a number of these hypothetical differences, and that is your hypothetical comparison distribution. So it's conceptually different and arithmetically different. So important is that you know how to recognize which one to use. How to calculate it, it's kind of easy, but needs to be kept in mind when actually executing the test. Good, so that's just a quick recap. Any questions on this? I think we've looked at this slide a couple of times, so I think you're quite aware of it. Okay, good. So now let's look at the example. And that's already one of these examples where basically you see already what clearly indicates we will be using a paired sample t-test. So pay attention and read the question carefully. So we have the following scores for 8 students. Yes. That's practice lab 3. Assignment. There's an assignment labeled in the homework tab. There's an assignment practice lab 3. That's where you can download the spreadsheet. Sorry, I should have. Did you find it? Yeah, good. Everybody found it? So that's the spreadsheet. Okay, so we have 8 students for 2 different exams. They have before and after exam. Did they get better or not? We want to know whether they improved significantly or not. We want to see whether the quote-unquote population has improved the performance. Good. As said, we will compare before and after. We do that with the 6 steps of hypothesis testing. We're doing this a little bit accelerated, and we're going to do this in Excel and R. We're calculating paired samples T statistics at an alpha level of 5%. We calculate a 95% confidence interval, and we calculate an effect size. Simple, right? Shouldn't be difficult. The only reason is like with practicing these things, you really get a solid handle on it. And if you do it, and this is where I think it's kind of the use of doing this in R and Excel, is if you see it in different softwares and you see what each software produces, it kind of gives a better handle on how to approach these things and gives more confidence in the conduct of statistics. Okay, exam 1, exam 2. We need a difference as the first step. We calculate the difference between those two. That's basically, exam 2 minus exam 1. Right, so that's a simple formula. We can pull this all the way down. Gives us these 8 entries. Now we calculate the mean. And so we calculate an average or mean. And this basically is average function of C4 to C11. I'm doing it a little faster for a reason, because I want to get as much covered today as possible, and also for you to have a chance to submit your practice. So we have here now these two exams. We have a difference. We have an average, which is 1.25. Doesn't necessarily scream like it's going to be significant, particularly.
One like formula for each of the differences, or like I have to put in each cell separately.
Yes, you will need to do that, but there's a way in Excel to automatize this. So if you calculate the first, you remember the thing with the little formula where you go on the right lower corner and you double click that. Once you double click that, it's going to do it for the whole thing.
How do I double click on that?
Okay, so you calculate here the difference.
Yeah.
Right?
Yeah.
And then you go to the right lower corner and you double click it.
Wait, sorry, I did it the wrong way. B4 minus.
Yeah.
Okay, yeah. Sorry.
And you double click in the right lower corner of that cell.
Oh.
Yep.
Cool.
Very cool.
Yeah.
Yeah, and very useful.
Very useful.
Yep. I highly recommend to keep that in mind, just like really memorize that. So these little things that I'm showing you that for a reason. Yes, please. How do you calculate the difference?
Yeah.
By calculating cell B4 minus A4. Okay, one thing I want to flag at this point, if you calculate an average of a difference, I'm just saying this, it may sound absolutely stupid of me to say that, but I just want to emphasize that. If you calculate average of all these differences now, that difference, this mean difference, needs to be consistent to building the average of exam 1 and exam 2. This difference is the same. So 80 minus 78.75 is 1.25, which is the same as the average difference. Some of you may look at me like I shouldn't be saying that, but it's just sometimes important to visualize that.
The second part equals the average of exam 1 minus exam 2, minus the average of exam 2.
This is a different way to approach this, yeah. So
I
you
don't
can,
have to, if I did the other thing, I don't have to do this.
both is the same. So you can you build the individual differences, or you calculate this minus this. It's the same value. It's sometimes nice to try those things out and to actually see it visualized. Okay, why is it still important to calculate the differences? Because this is a comparison distribution. So you still need these values. You need these differences to calculate now the standard deviation, right? So the standard deviation is now STDEF. We know this formula. STDEF of these differences gives us the standard deviation of these, which we know from the homework, right? So STDEF C4 to C11 gives us the variability within our differences. Those 8 differences build the variability of 5.7. The standard error of the mean, we know, is the standard deviation divided by the square root of the sample size, which we know is 8. So that's our standard error of the mean. Yep, ready. G5 divided by SQRT 8.
Why? Where did you get 8 from?
Well, it's 8 entries. Sample size. Sample size. Yeah, yeah. Sample size.
It's F5 divided by what?
F5, no, G5 divide, oh, F5, I don't know. Yeah. So it's the standard deviation divided by the square root of the 8. You remember that formula? ST divided by square root of the n. That's your standard error of the mean.
So
Okay.
it's G5 divided by, and then we'll check what it is.
Well, it's here. It's SQRT 8. That's your square root of 8. Good. 8, yes. 8 students. So if you have 8 students, what's your degree of freedom? So degree of freedom is 8 minus 1, right? So that's 7. So why do we need the degrees of freedom? Because in the T distribution, we basically determine our critical T by utilizing the degrees of freedom, not the sample size. We did that with the STAT statistic. Now we're using degrees of freedom. If you have a degree of freedom of 7 at an alpha level of 5%, you basically you determine the critical value to be 2.36. Why? Because we have degrees of freedom of 7. We go in row with the degrees, with corresponding degrees of freedom. And we are taking the column with a two-tailed hypothesis, a two-tailed alpha of 5% at a degree of freedom of 7 is 2.36. Right? We've done that. That's it. Well, then it would be 5% again, but it would be 1.89. Why? Because it shifts it on one side. Remember? The statistical power, you remember the slide? If you put it all on one side, you basically get that critically determined on one side only, which narrows it down. And you're more likely to exceed that critical T, thereby reject your null hypothesis. Yeah. Okay. Good. 2.36 on the two-tailed test. This is our critically T. Now the rest is simple. The only thing we need to do is critically T is now 2.36. Was that? Good. T is 2.36. That usually is it's the default. Let's put it that way. If not stated otherwise, you will assume it's a two-tailed test. It's like kind of 95% of all studies or analysis use two-tailed test. Only if there is a very specific, very specific research question, then you would use a one-tailed test. Bluntly spoken, you will have a very hard time getting that through the review process with a statistical reviewer. They are not going to like that one-tailed test. So you would really have to have a very specific question doing that. Yeah. All right. Sure. Okay. But again, one-tailed test, you put the critical T is all concentrated on one side. So you have the full 5% on one side, which is lowering your critical T closer to your mean. So your T will be lower than you need to exceed to reject the null hypothesis. Good. So 95% confidence interval, we know that already. So that's simple. So we have a lower limit and upper limit. Lower limit is our mean difference of 1.25 minus the critical T multiplied by our standard error of the mean. It's minus 3.48. I put the formula below. There's the formula. So lower limit is the mean difference minus G8 is the critical T multiplied by the standard error of the mean. So that gives you the lower bound of the 95% confidence interval.
What's G8 supposed to be?
Yep, G8 is critical T. G6 is the standard error of the mean. Yeah, come closer if it's easier. I wish it could. I wish I would have a greater screen. Sorry for that.
G6 is the standard. Oh, because I'm doing it on different.
Yeah.
On different things.
Yeah, it's like experience is different. I know.
How do we calculate the lower limit?
That's this formula right here. I zoom in a bit. So it's C14, which is your mean difference, minus G8, which is a critical T, multiplied by the standard error of the mean. That gets you the lower limit. So now when you're interested to calculate the upper limit, you take the mean difference and you add critical T multiplied by standard error of the mean, gets to 5.99, 985 something.
Mean difference. What is it?
That's the mean difference between exam 1 and exam 2.
And that's plus critical T?
Plus critical T multiplied by the standard error of the mean. Gets you exactly that interval within which your 95% confidence contains the population mean, and you know you can now basically make a conclusion about your alpha level, because this shows you exactly that range within which you're 95% certain that your true population dynamic of difference is. So now, if that is the case, we have here minus 3.49 and 5 plus 5.99. What can we conclude from that? It does contain the zero. It does contain zero. So your idea and your test, your null hypothesis is, maybe I shouldn't have skipped that. H0 is your difference is zero. Your HA, or alternatively, mean before equals mean after. Both are correct in that context. So you have difference equals zero, or your mean before equals your mean after. Means the same thing, but so now your HA is that the difference is different from zero, or your mean before is not equal to mean after. So that's your H0. So if now your zero is contained within a 95% confidence interval, you can basically say, I am not very confident that this is different from zero. I'm actually more than 5% certain it actually is equal to zero. So we are not exceeding, likely not exceeding our critical T. And we can bring that to the test by calculating our T. And this is, as we know, it's our mean difference minus zero divided by our standard error of the mean. So just for you to recall this, T-test 10. That's the formula. No, that's the effect size. Remember this? So that's the calculation. We don't have the T here. So you remember that example, right? So we have, I don't know what the score was about. What was the example? Yeah, those the news article, but it was associated with mental health violence. So we're calculating our T. We're getting our actual difference observed minus what we assume under the null hypothesis divided by the standard error of the mean. That gets us to the T. And this is the same thing we're doing here. So we're doing here difference, parentheses, difference minus zero divided by our SEM. And this in our case, this is 1.25 minus zero divided by our standard error of the mean. Gets us to a T of 0.62. It's simple, right? It's arithmetic. It's super simple to do. We have so with C15, which is our mean, minus zero divided by G6, which is our SEM. That's the difference. And the T-score. So this is simply done. If we want to know now a corresponding p-value, you can easily do that using in Excel the t-test function. So if we write out that function, t-test is the function, opens up with a parenthesis, and as soon as we have opened the parenthesis, we can click on fx, which opens the formula builder. Remember that formula builder. I highly recommend to remember that step as a take-home message. It's like, even if you don't need the calculation ever again, you will need them for the quizzes and the exams, but you will certainly one day in your life, you will need the t-test function. I guarantee you that. If you,
How do you do that?
it's equal t.test, t.test.
Yeah, and then you click on array one.
The formula builder here, the fx on the left top. So here you get prompted for 4 different entries. You need array 1, array 2, tails, and type. So array 1 is your first entry. So this is exam 1. Right? Array 2 corresponding exam 2 scores. Tails, we said we do a two-tailed test. So it's 2 for 2 tails. And then we need to determine the type. And this is a little trick here. So here we have 3 entries, and I think we talked about this last class, right? So we have 3 possibilities what to enter in. We can say it's a pair test, then we enter 1. We can say it's a 2-sample t-test with an equal variance, homoscedastic. Or thirdly, we can say it's a 2-sample t-test with unequal variance, which is heteroscedastic, equals 3. So we need 1 because we do a pair test, right? So we enter, here's the type, a 1. And we click on done. And the output here is the corresponding p-value. So the p-value is 0.55. What does that mean? That's a 55% probability that if you're saying this is significantly different from 0, you are committing a type 1 error. So you mean you're rejecting something that should not be rejected. So that's your type 1 error. So this is obviously greater than the 5% we were willing to accept. Therefore, we're accepting the null hypothesis, which we kind of knew already because our 95% confidence interval also contains the 0, which means there's no difference better than alpha 5%. Okay, simple, right? That's not super hard. Good. Any questions to that? It's kind of clear, right? And I will post the spreadsheet. You can review the formula. It's straightforward. It follows the same. Yes. All right. So let's go back. Let's go to the paired sample t-test. So if you have there was 2.78, I think there was a degree of freedom of, in that example, the degree of freedom was 2.78, and our degree of freedom was 7, critically T was 2.78. So we have now a certain range which constitutes a 95% confidence interval. We are hypothesizing under the null hypothesis that there's no difference with there's no difference to 0. So there was no change from before to after. To estimate this 95% confidence interval around 0, we are estimating these critically T values, right? So that means under the null hypothesis, we assume that there was no change. The difference is 0. We have a certain area around that within which we are 95% certain. That's a certainty of 95% that we're willing to accept. So if we find the mean of a sample, of a random sample that is, let's say, not exceeding that critical T, we are still confident about our estimate. If we have a sample that is beyond that, beyond this critical T, around that 0, and that exceeds this critical T, we have a certain probability that there is a difference from the sample mean to that hypothesized mean, null hypothesized mean of 0, or the difference of 0. So we're comparing the sample mean, the differences in scores, the difference scores, that mean of difference scores, to a mean or to a reference value of 0, where there was no change. Now, if you have something that exceeds this critical T, you're outside of that range. So your probability of this being different is essentially greater than 95%. So there's 1 minus 0.05. So if you do the opposite now, you calculate from a sample a mean and a mean of different scores, and you build your 95% confidence interval around that mean of different scores, you basically get now a 95% confidence interval around the mean. If this does not contain zero, you know that with accepting a certain kind of this estimation, you have still a significant difference. Sorry, at an absolute of 5%. So it really comes upon, this is an interval within which you're stating your confidence of this being different from whatever you're interested in. Because like I said, you can take zero, and you can build this 95% confidence interval. And that's actually how I got the very same question in the previous class. And so that's how I explained it there. So if you have a critical value, you have 2.36. You can calculate, okay, so let's say this is zero change. This is lower limit. This is upper limit. You can also take here zero. You can also say, okay, so I want the lower limit. This is this, which is zero, minus this, the critical t, multiplied by a standard error of the mean. Or I say, I want this plus the standard error of the mean multiplied by the critical t. So that would be this range within which around zero, I'm 95% certain that I would need to have. So that's basically the range where the null hypothesis is true. Well, what you have here, and that's your mean difference. Your mean difference now. So this is
equation for the lower limit.
yeah. So I'm trying to find out another way around to explain in the greater scheme of things. No, this is an explanation. You don't need to write it down. No.
Okay.
But just follow along with the thought process, because if you have minus 4.7 and plus 4.7, 1.25 is still part of your null hypothesis. So it's not exceeding this critical value. But if you would have a value greater than that, you would reject it. You would say that your sample is significantly different from your null hypothesis. And then you're rejecting it. And this basically everything exceeding that is 5%. 2.5 in that direction, 2.5 in that direction. And this is this graph. These are those 2.5%. So that's constituting those where levels are greater than that within are more extreme than those 95% under the null hypothesis. So this being said, this is exceeding. Our mean is not exceeding that range, and now we're doing the other way around. So the actual calculation of the 95% confidence interval is actually done around your mean difference. So this is basically built. This 95% confidence interval around your difference is built around your actual difference from your sample. And now you get minus 3.4 and 3.5 plus 5.9. And this does not contain the zero. So you're coming from the other way around. And if it doesn't contain the zero, it would be significantly different. In that example, it does contain the zero, therefore it's not significantly different, but we are accepting the null hypothesis, which is then, in addition to that, confirmed by a p-value that is substantially greater than 5%. So this is our certainty that if we would say we're rejecting it, it would be an error. So we are 55% certain that rejecting this would be an error. Make sense? Was that a... That is absolutely true. So we are not rejecting because we're considerably certain rejecting that would be wrong. So the rest risk you're willing to accept is only 5%. If you're rejecting something greater than 5%, you're violating that principle. You're basically accepting an alpha that is greater. We are 55% certain, not certain. The probability of rejecting something erroneously is 55%. So that's our probability of rejecting something we shouldn't reject if we were to reject this. You're welcome. Any other questions? I know it's just a concept. You got to think around 3 corners. I understand it's not easy, but you're not saying something is like that. You're just saying like that's my probability. It's not like that, right? So it makes it a little harder conceptually. But once you get behind the concept, the rest is easy. Once you know how to employ the concept, it's super easy. Okay. Good. So this was the calculation of our t-score. This is the corresponding p-value. Lastly, we just need the effect size. And the effect size is simple. That's basically just the difference divided by the standard deviation of our different scores, which we have here an effect size of 0.22, which essentially is, as we know, it's a small effect size. Not only small, it's a small and non-significant effect size. Yep. So we are checking out on this. So it's C15. It's actually C15. It would be C15 minus 0 because it's paired amplitude. So C15 minus 0. Our hypothesis divided by G5, which is our standard deviation.
What was C15 for you?
C15 is the difference. The difference.
So 1.25
1.25
minus 0.
Minus 0 divided by G5, which is the standard deviation.
That's the 5.67.
Correct.
Shoot, I got 1.25.
I got 0.
Is what?
I got 0.
No, come to 0. It's C15.
Is it 1.22?
So it's 1.25 minus 0, which is 1.25 divided by 5.7. Can't be 0.
My p-value is also wrong.
So let me put the formula there.
Oh, never mind. I think I just missing a digit. Mine ends on 5.
I will post the spreadsheet. You can correct the work afterwards. It's but I highly flag this kind of comparison. Keep that formula in the back of your head. You will need those again. There's a good chance you will need all this formula we're discussing in some shape or form. They're gonna come back to you.
Okay.
Good. All right. So that was the spreadsheet. Now we're getting to R. We're gonna do. So I've set up this spreadsheets, this script in a super simple way. So the only thing you need to do, you need to open it in RStudio. And if you go on the very first line, just have the cursor blinking there and press Control and Enter.
Wait, this is also on
Yes, it's on Canvas. That's the practice lab. That's actually the deliverable for the practice lab. So the only.
from R,
Hmm?
I don't see it on R, like on the practice lab thing. I just see the.
You have on Canvas, you have practice. It's not in the assignment, it's on Canvas, it's on the module. It's labeled practice labs 3 solution.r. Once you download that, open it with RStudio. Notably with RStudio, please, not with R. So, first line. You basically click in the first line, you press Control and Enter. So you run line 1, 2, 3, and 4. It's gonna jump all the way down to 4. RM list equals ls is clearing the environment. Was there a question? So you just click on the first line, you press Control and Enter at the same time. That gets you down to line 4. You can continue to press Control and Enter. That basically goes and runs line 6 and 7, which basically here creates your first data frame. Here on the right side, in the environment, you have now DF1. DF1 is the first data frame, and you can open this by just clicking on the little spreadsheet symbol here on the right. Opens the actual data frame. And this is the same data frame we just worked with. So this is just the data now in a different format, but it's the same data frame, exam1 and exam2. The assignments are the same. We calculate the paired sample t-statistic, we calculate the confidence interval and the effect size. So if you go down to line 12, you're running now your first t-test in R, which basically now gives you the results of the paired t-test. So it gives t-score of 0.62, which is consistent with what we've seen. We get degrees of freedom of 7, which we have seen. We get a p-value of 0.55, which is consistent with the p-value we just calculated in Excel. It also provides you with an alternative hypothesis of your test. It gives you a 95% confidence interval, which is consistent with what we've calculated. It does not contain 0. Therefore, we accept the null hypothesis, and it gives you mean of the differences of 1.25. So it's basically everything within a cell in like 20 different cells. R does it in one line of code. So that's the beauty of R. So that's basically this analysis that we've done. If we click now on line 14 and we run line 14, control and enter, does now something. It basically, data frames are being packed into objects. So df1 is the so-called object. If you, an object can contain data, an object can contain analyses, an object can contain text, it can contain models, whatever you want to pack. Now we're basically packing into t-test.df1, we're packing our t-test. And we're doing that for a reason, because if we created now t-test.df1, we have contained in this object now all these values that we have calculated, and we can extract all these values from our object. So if we want to, so here, for example, the standard error is the standard error we calculated. All this is contained now in this one object. If we're clicking now on LSDF1 in line 15, that is the list of sub-objects in our data frame, which is basically two variables, exam1 and exam2. If we do the same exercise in LSDF1, all these informations. We have estimates, which is our difference. We have standard error with p-values, with confidence intervals, with null values. We get all this information basically extracted from our test. And we can mobilize all this information from our t-test with basically one line of code, because line 17 mobilizes from this object the p-value. So 0.55 is the p-value that we calculate also in Excel. With our t-test function, we can do the same thing in our saved object of that t-test. So it's kind of elegant, and it's very useful if you write reports, for example, and you create tables. You can just call these and get those automatically inserted into tables or reports that you generate. That's actually, it's a very nice feature of R. You can program an entire report. And if you get new data in, you just get this data, you run the report again, takes you 30 seconds, and you have report updated. 30 seconds of work, that spares you hours of additional work. But that's for a different class. Okay, so we have with line 19, we can calculate now our 95% confidence interval, easily be extracted with t-test df1 conf int gets you the confidence interval. So it's very useful, right? So you get all this information quickly mobilized. You can also change the confidence levels. You can change it to different type 1 emphasis. Effect size is on line 21, which is the absolute mean difference divided by the standard error of our difference scores. Same as we calculated in Excel. Okay, so that's simple, right? So R is a useful tool for your analysis. So That was example number 1. If we're going back to Excel, any questions to anything of these our features that I've just walked this through? Yeah. Where again? Oh, no, can you point at it? Like the line number? Line 16, 17 would be here. This one? Yeah. So DF1 is the data set. That's this data frame. That's our exam scores. Whereas t-test DF1, that's the t-test. Well, run 15 and 16, they should give you 2 different results. Because 17, or no, 16, basically addresses t-test DF1. That's the actual t-test. Just try to run 15 and 16. They should both give you different results. 15 is referring to the data frame. 16 is referring to the t-test. Yeah? No? You keep getting 1. Can you run it again from line 1 up to 16? Just try that. Select line 1 to 16. That should not give you 1. If not, then you have some issue in there. Yeah, we need, okay. We can look at it after class, no problem. Yes. Yeah. Oh. So if you click here, you mean that? Yeah. Okay. So here it opens basically a different tab. So you can switch between these tabs by just clicking on the tab on top. Here on top, you have the tabs. Yeah, sorry. So that's t-test DF1. These are the different information in the t-test object. If you click on DF1, that's your actual data. And if you go on practice labs resolution R, that's your actual script. So you opened practice lab 3, right?
Yeah, no, I'm on it.
If you go to t-test DF1, there's a magnifying glass right next to it. If you click on the magnifying glass, it opens it up.
Yeah,
Okay. Okay.
I don't have.
Okay. Which stuff do you not have?
Yeah, I think that's what we know. Like where it says like alternative on the bottom,
On the bottom.
like the bottom section, like the console.
In green.
Yeah. Oh, well, it's green for us.
Okay, good point. Okay, like this.
Yeah, I don't have that.
Yeah, so you need to mobilize this. So if you go on line 16 and you run line 16, then you should have it. Yep. All right. How about you? No? Oh, okay, we'll find it later. Don't worry. Okay, good. Okay, so this was this. Any other questions with anything? Well, that's the first part of it. We have 2 more to go.
I have 3 lists of 10 in my global environment.
You have, did you run the whole thing already? Yeah, that's why. It's 2 more examples. So we're getting to those in the next, the next 15 minutes. Okay. Good. Back to the next example. So we're going to 1020. That's the second worksheet. Same principle, same test. It's actually so repetitive that we're almost gonna skip most of it. The only reason why I wanted to include it is because there's a slight difference, which you will notice in the results. So we're doing a difference. Same thing. We're doing score 2 minus score 1. We get a difference. We get now a mean difference, which is average. we're building mean difference. So we see that from exam 1 to exam 2, students actually get actually dropped this course. So there was a decrease in this course by 7.8 points. This may or may not be significant. We will see. How we're going to see that? We essentially calculate first. There would be a mean difference, yes. So we can, by calculating each individual difference,
yeah,
and then building the average of these 5 differences. Yep. So now we need to calculate the standard deviation, that is STDEF. And the standard deviation of these 5 entries are 6.14. We need, next, we need the standard error of the mean, that's 6.14 divided by 5, because it's 5 entries. Square root of 5. So that's 2.75. Now we need a critical T, which essentially with 5, degrees of freedom of 4 is 2.78. So critical T is 2.78. 95% CI. UL is minus 7.8. Minus.
Submit all this?
Do
Do you want us to submit all this?
No, just R.
Just R?
Don't worry. I will post this spreadsheet. I just want you to run the R.
Oh, but you're going so fast, I was like.
I know.
But you
No,
did it on the first one.
I'm just running out of time. That's why I'm
Okay.
rushing through a bit. But you have the recording, so that's you still can go through all the steps to practice and test your knowledge. So you're basically calculating the critical T multiplied by standard error of the mean. You have an upper limit by calculating the mean difference plus the standard error of the mean multiplied by the critical T. Yeah, it's the mean plus 2.78 multiplied by the standard error of the mean. That gets you to an upper limit.
So the order doesn't matter because you multiply by the previous.
No, it doesn't really matter because as per the rule in mathematics, always the multiplication will be first. So you basically, you first multiply that and then the result will be added, will be part of the addition. Okay, so if you look at the 95% confidence interval, it becomes clear that it doesn't contain the 0. Therefore, we will reject the null hypothesis. And the T, the actual T is now minus 7.8 divided by SEM, which is minus 2.84, which does essentially exceed, in a two-tailed hypothesis, exceeds to the negative. It's more extreme than our critical T. So minus 2.84 does essentially exceed 2.78. Therefore, it's significant at an alpha level of 5%. We can now calculate the p-value by essentially calculating t-test is now array 1, comma, array 2, tails of 2, because it's a two-tailed test, and we have a paired sample t-test, gets us a p-value of 0.046, which is 4.6%. It's smaller than the alpha level of 5%, which we're willing to accept. Good. Effect size is simply basically the difference divided by the standard deviation, which is minus 1.27. Keep in mind that even if it's negative, the conventions basically don't distinguish between negative and positive. You're basically looking at absolute value. That means even if it's negative in the two-tailed hypothesis, you will always drop the negative sign. So you have a large effect size essentially in that comparison between score 2 and 1. If yes. Yeah, we did. Minus 2.84. We calculated this by C10, which would be the difference. So it's the mean difference score minus the null hypothesis of 0 divided by our standard error of the mean. Gets us to minus 2.84, which is essentially our t exceeding the critical t to the lower end. Yeah. All right, going back to R, same code in essence. Line 24 creates this data frame, which basically contains these 5 observations for both variables, score 1 and score 2. We have a t-test for df2, which essentially is the same formula. So we have df2 score 1, we have df2 score 2, which is over 2. The only information that R needs to run this as a paired test is paired equals true. And then consequently, it will do this analysis for you. Will basically give you the same range of information as in previous example. It gives you a p-value, which is consistent with the p-value we quantified in Excel. And it gives you a confidence interval that is also consistent with what we have. And it gives you the t-test basically with the same results as we have, including the 95% confidence interval. The only thing pay attention, it's a two-tailed test. So basically it doesn't distinguish whether it subtracts score 1 from score 2 and score 2 from score 1. So this plays a role if you would extract the percentage data. Just pay attention that you understand in which direction R approached your data. It may be not in the way you want to present it in your data, so you can readjust that, but we can leave that out for now. Okay. Any questions to that? Simple, right? Same principle. It's considerably simple. You have some simple calculations that basically lead you now to your effect size. What's the other estimation of the effect size? And then lastly, we have the third example for the last 10 minutes. So here we have an interesting idea. So that's actually why I like the book from Nolan and Heinzen, because they actually have data from real psychological experiments. Actually, it's kind of an interesting idea. So they basically wanted to find out whether people that watch fiction on television have a changed perception of emotions of people. So they would basically make one cohort watch award-winning fiction and television like Mad Men and West Wing, and the other half they basically have to look at documentaries, and then they basically have these individuals grade and interpret people photos of people's eyes, and would need to decide whether the person was jealous, panicked, arrogant, or hateful. Scores ranged from 0 to 36 based on the number of emotions guessed correctly or incorrectly. So we have here 2 independent cohorts that will make us think independent sample t-test. We are meant to again calculate the same parameters of this statistic. So we're calculating first an average, which is the simple part of it. Which basically makes us already see with the naked eye that these 2 groups differed in terms of their perception. There was a difference that essentially was 1.5. So this would be this. So we have a difference of 1.5. Do we think this was significant? Well, we are asked to go through all 6 steps of hypothesis testing, but basically it's group H0 is group 1, mean 1 equals mean 2. Because HA is mean 1 is unequal to mean 2. So the rest of this basically can easily be evaluated with the detailed test function. And since this is the practice lab class, I think we can resort to basically using the t-test function, not calculated by hand. So if we have array 1 with basic Blasium, with A3 to A11, A3 array 2 would be B3 to B10. We again have 2 tails. And we have, and this with the type, it's becoming a little bit tricky because essentially we have 3 choices again. We have paired, which we know it's not. We have 2 samples with equal variance, homoscedastic. Or we have 2 samples unequal variance, heteroscedastic with 3. So what will make us think of unequal variance is essentially that we have different sample sizes. So we have 9 in one and we have 8 in the others. So that basically makes us think already 2 samples of unequal variance. So that would be 3. So with 3, we're getting to a t-score of a p-value of 3.7%. So this being said, we know that this perception is basically significant difference between both codes. Because the p-value is smaller than the critical alpha of 5%. So now let's quickly do this in R in the last 7 minutes. So if you open RStudio now, we're selecting now lines 38 to 39. Running this builds a 3rd data frame. And this essentially is, this, it looks the same way, but it basically it's the same data as in Excel. The only difference, and I just want to bring this to your attention, so there's one difference, is unequal length, unequal number of entries. What R does, because it's a different format than Excel, it presents data just different. What R does basically always needs equal length for comparison of such kinds. When you develop a data frame like that, it will always create equal length. What it creates here is NA. NA stands for not available and basically constitutes a missing value. This being said, this missing value will create a little bit of a hiccup if you don't pay attention to it. So you need to treat it carefully. Best example in this context is if you go on line 48, you basically get the same mean with the mean function that we have gotten in Excel, right? If you do this with mean documentary, DF3 documentary, and I'm just doing it for demonstration purposes. If I would do this with mean DF3 documentary, and I am disregarding NA, I get with this function, I get NA as a result. And that's unfortunately a problem because it will, as soon as an NA is involved, it will render the result, the statistic for the entire sample as NA. So therefore, you need to give an additional option to your mean estimate, which is NA.RM equals true, which basically removes that NA from the analysis. So control DF3 documentary NA.RM equals true will basically do the right thing and will result in the same estimate as in Excel. The same is true for the standard deviation. Basically, again, gives us 1.5 and 1.2. And with t-test DF3, t.test function of fiction versus documentary, this time not with the option of paired equals true, it will by default do a t-test, independent sample t-test with unequal variance, the so-called Wilks test. And this is basically what we see here. This is a Wilks two-sample t-test. We have a t of 2.3 degrees of freedom, and this is interesting. I just want to flag this because if you have 9 and 8, you have a sample size of 17 in both cohorts. And this is important to distinguish between a paired sample t-test and the independent sample t-test, because the degrees of freedom in a paired sample t-test is the number of different scores minus 1. If you have 2 cohorts or 2 samples, you basically, the number of all entries in both cohorts added minus 1 for each of those groups gives you the total degrees of freedom. So for 9 plus 8, 17, minus 2 groups, we're at 15. So the total degrees of freedom is 15. R does a different approach to that. It basically creates a mathematical function estimating the true degrees of freedom, which is slightly different from the rule of thumb estimation of 15. But that's a longer conversation to have. However, the p-value is consistent with what we've seen. It's 3.7%, which again leads us to the conclusion that this is significantly different, and the confidence intervals are basically consistent with what Axel showed. All right, so practice lab 3. The only thing you need to do now is to click on the console, press Control and L. You click on the editor, on the script, you press Command and A. You press Control and Enter. Just like the last time. And then the only thing you need to do is like you select everything from the console. You press Command and C. And you copy this over in a text edit file. You go on. Let me finish that for a second. I'm with you in a second. Then go on text edit. In text edit, you basically create a new document. You copy all your code from the console in, and you save this basically with the course number, your family name, and practice lab 3. Then you're all done. All right, thank you. Have a nice evening. I don't understand what. Sorry. Yes, Command L, yeah.
And then you command out. And then